Hello. So in this video, we're going to start our discussion about solving the heat equation and other PDEs on infinite domains, right? So all of our previous work, we've been focusing on, like a one-dimensional rod with coordinates 0 to L, or a string, kind of, again, coordinates from 0 to L. But there are a lot of problems where we would like to ignore boundary behavior, right? We just like to say, sure, the wave just goes off wherever, what's going to happen, or heat's just going to dissipate kind of wherever, what's going to happen. So in this section, we're going to start a discussion by looking at the heat equation on an infinite domain. And this is going to let us set up some of the building blocks kind of around what Fourier series and this Fourier analysis looks like for kind of infinite intervals. Yeah. So the things that we're going to talk about here is just, first of all, setting up kind of what the heat equation looks like on an infinite domain, as well as a short discussion of the boundary conditions. Then we're going to turn back to separation of variables, seeing what that looks like in this context. We're going to solve an eigenvalue problem. We're going to sum up these solutions, kind of using a principle of superposition. And then we're going to look at kind of complex kind of exponentials and kind of the complex version of all of these solutions. Okay. Cool. So what does a heat equation look like on an infinite domain? Well, what do we mean by infinite? So here, we're going to be focusing on this PDE, right? So the usual heat equation, one time derivative, two spatial derivatives. And the domain of interest, right? So keep in mind here, U is a function of both space and time, okay? So previously, right, space was between 0 and L. Time, we said, start at time 0, go off forever. So here we're going to say, well, time can still go off to infinity, right? So the interval for time is 0 to infinity. But now space, we're letting kind of be from negative infinity up to infinity. Okay, and so this is what we mean when we say an infinite interval, right? Otherwise, yeah, so here's our PDE. We also need an initial condition and boundary conditions. So our initial condition, we're saying, well, what is the distribution of temperature, right, on this infinite real line? Well, it's some initial function f. But now comes the interesting bit, right? Well, what should our boundary conditions be? Okay. And so kind of related, the question is, well, what even is the boundary of this infinite interval? Okay. So for us, the boundary is going to be what happens. So I can write it here. So boundary for us is what happens as x goes to infinity. Okay. So in practice, we'll write, right, u, our solution function evaluated at plus or minus infinity, right? We're not really kind of plugging in infinity, we're just taking the limit, okay? But for us, our boundary conditions will be, well, what happens as you head off to infinity, okay? So in practice, we don't usually say these boundary conditions at infinity are usually implicit. Physically speaking, we'd expect that the temperature, right, as you go to plus or minus infinity, we'd expect that the temperature tends to 0, right? Something about a finite amount of energy in the universe. And so if you walk far enough away from a heat source, you're not going to be feeling any of that energy. And so the limit as x tends to positive or negative infinity of the temperature should be 0, okay, irrespective of time. And so one thing to note is that just because the temperature goes to 0, if you compute the total thermal energy, then total thermal energy may not be 0, or sorry, may not be finite. right? And so as an example of this, suppose you take some function that looks like, so out here, this is going to look like 1 over x. Out here, this is going to look like 1 over negative x. And then maybe in the interior, it looks something like that. So it's smooth, whatever. But the point is that this function is integrable. So the total energy, from negative infinity to infinity, of, say, this temperature, this is going to be something like maybe some constant corresponding to what's happening in here, plus twice the integral from, maybe we'll say that point is L, that point is negative L out to infinity of 1 over x dx. Right, so what we're doing here is we're saying, well, what is this total energy, right? That's what we get by integrating all of this. How do we integrate it? Well, it's whatever the total energy in this bit is, plus whatever the total energy out here is. And say, because this is symmetric, the total energy here is a total energy over here. Okay. Yeah, so the total energy for this whole thing, we can compute as whatever is in here plus twice whatever the energy here is. Okay. The energy coming from here is going to be the integral from L to infinity of 1 over x. Right? But this integral is approximately, right, we'll write ln of infinity minus ln of L, right? And this thing goes off to infinity. So here's an example where, right, even though the temperature goes to 0, you can still get an infinite amount of total thermal energy. Okay? But this isn't something that we're really going to worry about. We're just going to assume everything's as nice as we could ever want it to be. Okay. And so in practice, we're just going to stick with, right, further away you get, less energy you're going to feel. So as you get far enough away, energy is going to be 0. And so kind of our effective boundary conditions will be temperature at negative infinity, no matter the time, it's going to be 0. Right? But in practice, this means, so this means the limit as x goes to minus infinity of u of x comma t, this is 0, okay? But yeah, so in any case, boundary conditions are u at minus infinity comma t is 0, and u at infinity comma t is 0. Okay. Cool. So now we have spatial boundary conditions. We have an initial condition in time. So now let's apply separation of variables, right? The kind of same technique we've been using for almost everything. Let's apply separation of variables and start constructing solutions to the heat equation in this geometry. Okay, so as before, we're going to set u of x comma t. We're going to look for a separated solution. Okay, and so recall, so the PDE was du dt is k d squared u dx squared. Okay, so plug in u of x comma t. What we're going to end up with is dh dt times phi is equal to k d squared phi dx squared h. Okay. Move the kh down there, move this phi down there. You're going to end up with this business. Both sides are equal to some constant, and that constant we're going to call minus lambda. Okay. And so breaking up this equality, we have two kind of ODEs that we end up with. Okay. Cool. Right. And so as before, what we're going to do is we're going to say, well, we have spatial information. Okay. So let's try to figure out what solutions there are to this ODE, figure out what possibilities for lambda there are, and then plug those back up in there and then solve for h. Okay. So what happens? Well, so, right, as we said, boundary conditions for u of x comma t were, right, the solution tends to 0 as you head out to positive or minus infinity. Okay. So the question is, does that translate to phi, right, just the spatial piece of our separated solution, is that going to be 0 at minus infinity and infinity? Well, let's take a look. So for, let's see, lambda equals, we'll say lambda is positive. Okay. This means that b of x is going to take the form c1 cosine of root lambda of t plus, this should be of x, plus c2 sine root lambda x. Okay. And so limit as x goes to, say, plus or minus infinity of phi of x, right? Well, here, both of these functions are periodic, right? So as x goes to plus or minus infinity, cosine and sine, they're just going to oscillate between two values. Okay, so this limit doesn't exist. Okay? So already we kind of have an issue, right? We would like to say kind of spatial piece is oscillatory in some sense and kind of build up Fourier series from those building blocks. But if these are the boundary conditions we're using, right, that phi needs to go to 0 or be 0 as x goes to positive or minus infinity, well, already cosine and sine don't work, right? Because for this phi, this doesn't hold. Right? Likewise, if lambda is negative, phi of x is going to take the form c1 e to the root lambda x plus c2 e to the minus root lambda x. Okay. As x goes to positive or minus infinity, right? One of these two is going to go to 0. The other one is going to tend to infinity. Okay. So if you take this linear combination, right, to impose that we need the limit as you go to minus infinity and positive infinity to be 0, well, that forces C1 and C2 to both be 0. Okay. So right here, that C1, C2 is 0 based on these boundary conditions. Okay. Likewise, if we say, okay, so up here, if lambda is 0, then phi of x, this is going to be C1x plus C2. Okay. Limit as x goes to, so if C1 is non-zero, right? Limit as x goes to infinity of phi of x here, this will be non-zero. Okay. So you must have that C1 is 0. Otherwise, we have phi of x equals C2. Okay. And again, if we want the limit to be 0 as we go out to positive or minus infinity, well, what must be true of this constant function? C2 is 0. Okay. So in this case, right, if we focus on this ODE and we break it up into cases, right, lambda positive, lambda 0, lambda negative, construct the solutions and look at the limiting behavior, we see that, well, if these are the boundary conditions we want to use for phi, then we don't get any non-trivial solutions. We don't get any viable solutions. Okay. So the takeaway is that, right, so does this mean the boundary conditions for phi are phi of minus infinity and positive infinity equal to 0? The answer is no, they don't work. So how do we get around this? Well, turns out that asking phi to be 0, right, the spatial piece, if you go out to positive or minus infinity, that's actually asking for way too much. Okay. Instead, we can just ask that phi is bounded, right? So as you go out to plus or minus infinity, take the absolute value of phi, whatever this quantity is, it cannot diverge. Right, so here we're saying the limit as you go out is finite. Another way to write the same thing is just plug in plus or minus infinity. Those values have to be finite, or phi of x is bounded as you go out to plus or minus infinity. Okay, and so it turns out that, right, using these spatial boundary conditions, everything's consistent. It works with the rest of the framework, etc. Which we'll see by actually constructing solutions and verifying that they do work. Okay. Oh, and one thing I'll note is that, okay, so here, right, if we go back and we say, okay, well, for example, if lambda's positive, then phi of x, this was C1 cosine of root lambda x plus C2 sine of root lambda x, right? Absolute value of phi is finite for all x. So especially as x goes to plus or minus infinity, just because cosine and sine, they oscillate between +1 and -1. Okay. So with these boundary conditions, lambda positive is a viable solution. So let's look at this a little more in depth. So now we're actually going to go back and solve this eigenvalue problem with these boundary conditions at infinity. Okay. Right, so move things around. This is the ODE we're working with. What are the boundary conditions? You need the function, the solution to be bounded as you go out to plus or minus infinity. And so what we'll see is that then, okay, possible eigenvalues or eigenfunctions are, well, if you plug in lambda equals 0, right, solve for this, you're going to get, so lambda equals 0. What do you end up with? D squared dx squared phi is 0. So as we saw before, phi of x is C1x plus C2. For this to be bounded, C1 has to be 0, so we end up with a constant, right? So in this case, lambda equals 0 is a viable eigenvalue, and the corresponding eigenfunction is a constant, C2. Likewise, for lambda positive, as we saw on the other slide, this is a viable solution because it's bounded. It also solves this ODE, okay, and we're good to go. Lambda negative, phi of x equal to C1 e to the root lambda x plus C2 e to the minus root lambda x. This doesn't work. Again, because either direction you go, right? So if you go to positive infinity and C1 is non-zero, you're going to get something like that, which is going to tend to infinity. Okay, so C1 has to be 0 because we want the that limit to be finite or bounded. Likewise, consider what happens with C2. Well, here we have an e to the minus root lambda x. So this is going to look something like that. So if we go to negative infinity, then over here, that's still going to go to infinity. Okay, so point is, if our boundary condition is that the solution is bounded, then lambda 0, lambda positive work, lambda negative doesn't work. And we can explicitly write out what the solutions look like. Okay. Right, so one thing to note is that, well, every possible lambda positive works, right? And not just lambda of this form. Okay. because you can go back here, right? Plug in whatever you want for positive lambda, take two derivatives here, you're going to end up with negative lambda phi, right? So no matter what real number you plug in here, this whole thing solves this, and it's also bounded, okay? So every possible positive real number is an eigenvalue. And so because of that, we say that this eigenvalue problem has a continuous spectrum, right? The possibilities for plugging in whatever for lambda, right, they form a continuum versus before when we could parameterize them by integers, n, okay? Before we were working with the discrete spectrum, now we're working with the continuous spectrum because every lambda works. Okay. Cool, so we figured out what possibilities there are for lambda, right? Every possible positive lambda works, as lambda equals 0, okay? And so if you go back, I can go back a few slides, what is it here? So we said is, well, here, every possible lambda works. So go back here, solve for h, you're going to end up with exactly e to the minus k. Oh, that's a typo. This should read one second. Every possible lambda works. And so if we take two derivatives, then this should be, one second. No, here we're just taking one derivative. So we want up here, it should be no square. There we go. This is what you get by solving the ODE in time when lambda is positive. Otherwise, when lambda equals 0, you just have dh dt is equal to 0. So h is going to be a constant. Okay. So in this way, we figured out what our spatial and time pieces are. Okay. And so now we need to look at the issue of superposition. Right before, we just had a discrete number of, or a discrete collection of eigenvalues, right? Well, then we had a discrete collection of eigenfunctions. Okay, so for each of those, we multiplied by this, sum them up, we were good to go. Okay, now we have a continuum of them. So how do we sum them up? Like, what's the continuous version of summing them up? Right, well, so in this case, summing them up is going to become integrating them up. Right, so before we had these discrete building blocks, multiply each of these by the corresponding time piece. So what we ended up with was a constant, right? So our solution to the heat equation on a finite domain, this was a constant plus some coefficient for the sine terms plus some coefficient for the cosine terms. Okay. So now, since we don't have, right, discrete eigenvalues and the corresponding coefficients depending on these eigenvalues, since now we have a continuum of them, instead of summing them up, we're going to replace this with essentially an integral over the entire domain of eigenvalues we care about. So we'd expect that the integral or integral is going to go from 0 up to infinity, where we're integrating over the possible eigenvalues. So the integral is going to be something like d lambda, right? Summing up over these this continuum of eigenvalues. So let's see what this looks like. So, as I mentioned, right, our solutions now they depend on this continuous parameter, right, lambda. So in place of a summation, we have this integral from 0 to infinity, where, right, we have this cosine term, right? Sure, times our spatial term, or sorry, times our time piece. But corresponding to our cosine term, we have some coefficient depending on our eigenvalue. Likewise, we have our sine terms that we got from our separated solution times some coefficient depending on our eigenvalue. Right, and here we're just integrating over all possible eigenvalues. Okay, so one kind of annoying thing is, well, we have a square root here, a square root here, and a non-square root there. Because we have a continuum of lambda, it doesn't really matter if we take a square root. We're just going to get a different positive number. So in practice, what we do is we say, well, this is just going to be some other number. So we write this as we sum up over these parameters omega, right? So sum up over omega. And so we have some coefficient depending on omega times the corresponding cosine term depending on omega times the corresponding time piece also depending on omega. Okay. So if you wanted to make this precise, you could kind of do a change of variables formula where you say what omega is omega is lambda squared. Is that right? No, my bad. Other way. Omega squared is lambda. So what is d lambda? This is going to be 2 omega d omega. Differentiate this, bring the 2 down, etc. Okay. So plug this in there, etc. And then plug this in for d lambda. You're going to get the d omega. You're going to get this omega squared, omega. Okay. Now what we're going to do though is we're going to distribute this 2 omega to each of these terms. So maybe a slightly better notation would have been, right, this is a tilde, b tilde, where a tilde of omega, this is 2, let's see, 2 omega a of omega. Okay. Right, but the point here is this is just some other constant or some other coefficient in front of this cosine term. Okay, so in practice, it doesn't really matter how we normalize. But anyways, yeah, okay. So for superposition and solving the heat equation, this is going to be kind of our general solution. Right? This is going to be the superposition of some coefficient times our cosine term times our time piece plus some sine coefficient times a sine term times our time piece. Okay, and we sum them up over every possible eigenvalue parameterized by omega. Okay. So one question is, well, how do we compute these coefficients? We'll talk about that, I think, in the next section. Okay. But one observation we can make right away is that, well, whatever these coefficients are, a of omega and b of omega, they need to kind of satisfy this initial condition, right? So in our PDE, we were given this initial condition where, right, the temperature distribution at time 0 was some function f of x. So if you plug in back here, so if you plug in t is equal to 0, you're going to get a 0 there, a 0 there. This is going to be 1. This is going to be 1. Okay. So what we end up with is just the integral of a omega cosine of omega x, b omega sine omega x. And that's equal to u of x comma 0, which is equal to f of x. So whatever these coefficients are, they need to satisfy this equality, where this should be a d omega. Okay. And so here already we're getting kind of an analog of a Fourier decomposition, right, for a function f. This time the decomposition isn't in terms of, right, a Fourier series where we're summing up these sine and cosine terms. Now we're, right, integrating over a bunch of sine and cosine terms. Okay, but it's the same idea, right? We're decomposing f into a certain representation based on cosine and sine functions. Okay. Cool. Okay. Great. So that's all well and good, and especially, right, keeping everything in the real setting, it matches up with our experience and our comfort working with sine and cosine, etc. So now the question is, well, what does all of this look like if instead of using, right, sine and cosine, we use complex exponentials? Okay. So we can go back, we can start from this ODE, right? Kind of use that standard technique from ODEs, right? You're going to get, so if phi of x is e to the RT, this gives us that, well, e to the RT times what? R squared plus lambda is 0. So R squared, it's going to be plus or minus. No, come on. So R is going to be, come on, plus or minus square root of minus lambda. Okay. Is that right? Yep. Okay. And so if lambda is positive, then we can write this as R is equal to plus or minus I square root lambda. Okay. And now since lambda is positive, we can take the square root, no problem. Otherwise, we pulled this minus 1 out. And so that's where that I is coming from. Okay. Right. So this tells us that, right, what are these complex solutions? Phi of x, this is going to be C1 e to the I square root lambda x plus C2 e to the minus I square root lambda x. Before, what we did is we broke each of these terms into sine and cosine pieces, played around with the coefficients so that everything was real. But now we're going to keep them as plus or minus I square root lambda. Okay. Right, so as we just computed, here are solutions. This is our general solution to that ODE. And again, doesn't matter what lambda, as long as it's positive, this is solved. Okay. And so again, what we're going to do is we're going to, right, kind of by superposition, we said u of x comma t, this is time piece times spatial piece. H we computed to be e to the minus k lambda t. Phi we computed to be kind of the superposition of C1 ei root lambda x plus C2 e to the minus I root lambda x. Okay. And so now summing up over all of these, right, that becomes this integral, right? For some coefficients, depending on, in this case, omega, but we're summing up over some coefficients times our time piece times a corresponding omega. Okay, and so keep in mind that here, right, we have plus and minus square root lambda, which is omega. And so in a sense, technically, when we're doing the superposition, what we're working with is the integral from 0 to infinity of c of omega e to the minus k omega squared t e to the I omega x d omega. That's just summing up over these positive pieces. Plus, we also sum up over the other half, and we're just going to write everything exactly the same way. Minus k omega squared t e to the I omega x dx. Right? We're now kind of, this integral is a superposition for these pieces. Right, because essentially we have the same coefficients and same functions that are appearing in each integral, combine the bounds or combine the integrals via their bounds, and we end up with this expression here. Okay, but the point is the same, right? It's this continuum analog of superposition, right, where we're summing up over every possible eigenvalue to construct our solution. Okay. Right, and we can compare it to what we had before, just piece by piece. That's and so if we want this to satisfy the initial condition as well, right, we'll plug in, actually I should do it here. So plug in t equals 0 in there. This becomes 1, so we're left with c omega e to the I omega dx, which is kind of the another version of our kind of this Fourier representation. Okay. Cool. So that's the introduction. Kind of in the next section, what we're going to do is say, well, great. If we kind of work with these objects, sure, they satisfy the PDE, which you can verify just by taking derivatives, plugging in, seeing what happens. Question is, how do we actually compute these coefficients c omega as well as a omega and b omega? Okay. And so that'll be the topic of the next section.